Broadcasting is the mechanism through which Numpy performs vectorized operations on arrays of different shapes and sizes. Now, for broadcasting to work, two arrays have to be compatible. So usually we compare the shapes of the two arrays. So we start from the right, which is the last dimension. We move to the left, which is the first dimension. Now, two arrays might become compatible only if one, their dimensions are equal, and then two, one of them is 1. So broadly in broadcasting, we follow these two rules. So let me show you what I'm talking about. So here we say for two arrays to work together, we compare their shapes starting from the right. So that's the column dimension, which is the last dimension. And we move to the left, which is the first dimension, that is the row dimension. So those the two dimensions are compatible only if rule 1 is their dimensions are equal, and then rule 2 is one of them is 1. So for broadcasting to work, both of our arrays have to satisfy these rules. So I have an infographic here. Now look at this example. We have two arrays of different shapes, and then we're trying to perform arithmetic addition operation on the two arrays. So these are two-dimensional arrays. So when we had this array plus this array, we got array with this shape. Now this is how it worked. Look at A, 5 by 1. B, that is array B, 1 by 3. So we start from the right. This is 1. The column dimension is 1. The column dimension here is 3. Now the rule says either their dimensions are equal or one of them is 1. So in this case, one of them is 1. So this is yes. This agrees, this satisfies one of our rules. The second, on the left, which is row dimension, the first array has 5. The second array has 1. Again, these satisfy one of our rules, which is one of them has to be 1. So these two arrays, according to our rules, are compatible. So our two arrays have to satisfy one or both of the rules for them to be compatible. Now here we got 5, 3. Well, how does this work? This is 1, this is 3. One of them is 1, so this is yes on this dimension. So what Numpy does is it stretches this. This is on the column dimension, so it stretches this horizontally to fit with this 3 such that this becomes 3 in the course of the stretching. Now this is 5, this is 1. So Numpy stretches this on the row dimension. So it stretches this vertically to fit with 5. So that at the end of the day, we get 5 and 3. Let's look at another one. This is another one. We have two arrays. This is array 3 by 4. And then this array is just 4. So this is two-dimensional array. This is one-dimensional array. So what Numpy does with this 1D array is this 4, it moves it to the right. Okay, so it moves this to the right, which is the column dimension. And then it prepares the left with 1, the row dimension, such that this now becomes 1, 4. This retains its shape. So this is A, this, we have 3, 4. Now this, we said Numpy will move it to the right, this 4, and then prepares left with 1. So 4 is on the right. Here you're going to have 1. So when you look at our rule, look our two rules, we start from the right. These two dimensions are equal. 4, 4. So this is yes. Now on the left side, this is 3. This is going to be 1. Remember, we said one of the dimensions has to be 1. So this is 1. So this is yes on the row dimension. So what Numpy does is it stretches this 1 to fit with 3. So at the end of the day, we have 3 by 4. Let's look at another one. Now this is 3-dimensional array plus 2-dimensional array. So we have 2, 3, 4, 3, 1, and then we got 2, 3, 4. Now how does this work? We have 2, 3, 4, 3, 1. So 3, 1, Numpy prepends the leftmost part with 1. So this is 3, 1, 3, 1. There is one space here. So Numpy will prepend this place with 1 such that this will become 1, 3, 1. Now we have to apply our rules. Either the two dimensions are equal or one of them is 1. So here we have 4, 1. So this is yes. Remember, we always start from the right hand side. So 4, 1. Numpy will stretch this to 4. So this will be 4. 3, 3. There's no need for stretching. They are equal. So that's 3. 2 here, 1 here. Numpy will stretch 1 to fit with 2. So then we have 2. So the resulting array after computation will now be 2, 3, 4. I hope you guys understand what I'm trying to explain here. Okay, now let's go to our IPython and play with some examples. All right, now I'm going to start with scalar broadcasting. So let's have A equals np dot array. So let's have this. So that's our, oh, I'm sorry. Why do I always forget this? So I should have imported import numpy as np. So I should have done that. Apologies. So now we can have A equals np dot array. So that's our A. Now A dot shape is 5, comma this. Okay. So remember what we said. Look at this. Numpy will reshape A such that A becomes 1, 5. So that's what Numpy will do. So Numpy will move this 5 to the right and then prepares the left with 1, like that. Now, say we do something like A plus 5. I don't want to press enter yet. I want to explain something. Now, 5 is not an array. 5 is just a scalar entity. So with this 5, what Numpy will do is this. Because it is not an array, now Numpy has reshaped this to be 1, 5. Because we only had 5 here. So Numpy will move this 5 to the right. Remember we said we always start from the right. So it will move 5 to the right and it prepares the left with 1. Okay. Now we're trying to add this 5. 5 is a scalar entity. It's not an array. So what Numpy will do is Numpy will take 5 and okay, and then assigns shape 1, 1. So we're trying to add 5. So we're trying to perform scalar broadcasting. So NumPy we take this 5 since it's not an array and assigns the shape 1 1 such that when we start on the right 1 5, one of them is 1, so NumPy stretches this to 5, and then 1 1, so there's no stretching here, both of them are equal. So that when we now perform our operation, the resulting array is going to be 1 5. So let's go. So if we do a plus 5, see, we get 1 5. Although if we check for the shape of this, we get 5. But then this is what NumPy is doing. So we get this 5 7 8 9 10. So this has been stretched to 1 5. This scalar entity. So even if we do a multiply by 5, it doesn't matter. We could even do a multiply by 10. It's the same thing. NumPy will do as it did for this with 10. Like that. Even if we did a divided by 5. So you see, there are no loops here. The operation is done element-wise, all at once. So we can even do floor division. 10. See? 0 0. Like that. What else can we do? We can even do what is it? Can even do modulus operation 5, like that. So this is scalar broadcasting, guys. Good. Now let's look at 1 dimension plus 2-dimensional array. Now if we do, let's do b equals, we had an example of what 1 dimension and 2-dimensional array would look like here. So let's demonstrate that here. So if we had b equals, I'm going to do the first dimension. So let's go with this. Let's go with this. We had 4, and then we had 3 by 4. So let's go with this example. For 4, we could have NP. So like that. Then let's have C equals, I think, and that was 3 by 4. Okay. So now let's do NP dot arrange. Let's start from 1 and 13. So that's going to give us 12 items. So we can reshape 3 by 4 like that. Oh, I think I made a mistake. I'm sorry, my spelling is wrong. Sorry. So C reshape, okay, 3 by 4 like that. Now if we look at b dot shape, that's 4. Okay, so b dot shape 4. So what is going to happen is NumPy, we assign shape 1 4 to b like that. So now let's look at c dot shape 3 by 4. Okay, so NumPy will move this to the right and it prepares the left with 1 such that it become 1 by 4. I'm talking about the 1-dimensional array now. So this is going to be 1 by 4 during broadcasting. Now we start from the right. 4 is on the right here. 4 is on the right. The dimensions are equal. So that's yes. Here we have 3. We have 1. One of them has 1. So NumPy will stretch this one to become 3. So at the end of the day, we should have 3 by 4 operation in whatever we're trying to do, such that if we do b plus c, so we have 1 2 3 1 2 3 4. It doesn't matter. We could have done b multiplied by c. We will still get what is it called? We'll still get 3 by 4 dimension which is a 3x4 shape, 2-dimensional array. We could even do B divided by C. See, it's the same thing. We're going to get 3x4. So that's for 1 dimension plus 2-dimensional array operation. Now let's look at the third example here, where we had 3-dimensional array plus 2-dimensional array. So let's look at this. 2, 3, 4, then 3, 1. Sorry, guys. So we have 2, 3, 4, which is the resulting array after this operation. So we go from 3-dimensional array, which is 2, 3, 4. So we have depth or layers of 2. The rows are 3, and then the columns are 4. So let's try to create this, and let's see how this works. 2, 3, 4. Okay. So let's go here. Let me create space. I want to clear this. Okay. We already imported Numpy, so then we can do what should we do? Let's do array 3D. Okay, if I did 3D, no, that doesn't work. Array 3D. Okay, so this I can do np dot arrange 2, 3, 4, right? 2, 3, 4. So that's 9. Okay, so let's do 9. We can do 1 to 10, and then we can do reshape 2, 3, 4. What did I do wrong? Cannot reshape array of size 9 into shape 2, 3, 4. Okay, I went from 1 to 10. Oh, I'm sorry, that should have been 1 to 11. So let's take that again, and then instead of 1 to 10, so let's do it at 11, so that it goes from 1 to 10. Five, 9. Okay. I've learned that again. What is it? Cannot reshape array of size 10 into shape 2, 3, 4. Oh, what am I doing? 2 times 3 is 6. 6 times 4 is 24. Apologies, I was hiding. I have to redo this. So this should be 24, right? So I should go 1 from 1 to 25. Sorry guys, I was adding, I've forgotten. Okay, so that's our 3D. And then for our 2D, we had what did we have? We have 3, 1. So that's 3 times 1, 3. Oh, I was adding. So np dot arrange. Let's go from 1 to 4, so that we can reshape 3, 1. So essentially, I think this is going to give us a column matrix. Okay, so let's do a 3D. What do we have there? Good. So we have a 3-dimensional arrays, depth of 2, 1, 2. So we have 2 layers. Remember, we had 2, 3, 4. Now the 3 refers to the rows 1, 2, 3, which is the vertical axis. And then for our column, we have 4, 1, 2, 3, 4, which is the horizontal axis. Okay, so that's for our 3-dimensional array. Now let's look at our 2-dimensional array. A 2D. So this is a column matrix. 1, 2, 3, 1, 3 by 1. So we can do a 3D dot shape. So this 2, 3, 4, and then we can do a 2D dot shape, which is 3, 1. So for this to work, what happened is Numpy, we move 3 and 1 to the right, and then prepares left with 1. So let's go back here. So we have 2, 3, 4, 3, 1. This Numpy is going to prepare this with 1. So we always start from the right. 1 is there, 4 is there. So one of them is 1. So this agrees with our rule. So Numpy will stretch this to be 4. And then the resulting dimension is going to be 4. 33, they are equal. So we have 3. 1, 2, 1 is going to be stretched to 2. So we're going to have 2. So the resulting array is going to be 2, 3, 4. So then if we go back here and then we do a 3D plus a 2D. So at the end of the day, we have 1, 2, 1, 2, 3. That's 2 by 3, 1, 2, 3, 4. So 2, 3, 4. What is it? 2, 3, 4. That's the resulting array. So we can even do result equals a 3D multiplied by a 2D. So if you go result, so we get this. So we can do result dot shape. So we get 2, 3, 4. Okay. So what else can we do? Let's try some outer products via broadcasting. So in this approach, we're going to use np.newAccess. So what np.newAccess does is it reshapes our arrays inline to trigger broadcasting, which offers a powerful pattern for computing pairwise combinations. So let's try to implement outer products. So we can have let's have x, and then we can have np dot. Okay, before we go into this, if we try to do something like this, for instance, I want to show you how this does not work. This broadcasting thing. Say we have what is it called? So we have I don't know, test, and then we have np.arrange, and then we have 9. It's going to give us 8.reshape, and then we have 2 by 4. No, 2 by 4. What did I do again? Cannot reshape. 2 times 4 is 8, and this is 9. It goes from 0 to 8. Oh, sorry. This should have been. So 2 times 4 is 8. Okay, it starts from 0. My bad. Sorry. Test equals np.arrange. This should have been 8. So it's going to stop at 7, and then it starts from 0. So we get from 0 to 7. All right. So if you do test.shape 2 by 4, all right. Now we have 2 by 4. Now let's say we do, I don't know, let's say we do p equals, we do np, okay, and then we now do 5. So p dot shape, that's 5. Now usually Numpy will move this to the right, and it prepares this 1. So we have 1, 5, 2, 4. This is not going to work, because on the right now we're going to have 5. 5 and 4 are not equal, and neither of them is 1. And on the right, even though we have 1 now, 2 here, which agrees with our rule, it's still not going to work because 5 and 4, they are not equal. Neither do they contain 1. So if we try to do test plus P, for instance, it's going to blow up. See? It says operands could not be broadcast together with shapes 2, 4, 5. So, guys, bear that in mind. Our 2 rules have to be satisfied, or one of them has to be satisfied. 1 or 2 have to be satisfied. So, in this case, 5 and 4 does not satisfy, even though 1 satisfy. But then remember we said is either both of them, the dimensions are equal or the same, or one of them is 1. So even though 1 is here, the other one did not work. Okay. Now let's go to our outer product. We have x np dot array. So this is 1, 2, 3, 4. Okay. Now we can do y equals np. Okay, we can do something like this, no problem. So this is 1, 2, 3, 4. This is going to be shape, what is it called? Shape 4 or size 4, okay? And then Numpy is going to prepend, but then this is 3. Okay, you might think, this is not going to work because, but what we're trying to do is we're going to use np, the new axis, to reshape this such that they work. Okay, so let's have that. Now let's look at outer x. For outer x, let's do slicing x, and then we have this, and then we do np dot new axis, like that. So what this is saying is add dimension of size 1 to the column axis. That's the point of this np dot new axis. So it's going to take this. We're applying what is it called? Slicing now. So the first axis remain as it is. So Numpy is going to add a new axis to the column axis. Okay, so we can do this, and then we can do outer y. So essentially, this is going to form a I think this is going to form a column axis, if I'm not mistaken, and then this is going to be y, and then we can have np the new axis, and then the row stays as it is. So what this is doing is Numpy is adding a new dimension of size 1 to the row axis. Okay, so this is adding a new dimension of size 1 to the column axis. This is adding a new dimension of size 1 to the row axis. So let's see what we have. If we do outer x, so like we said, since it's adding a new dimension to the column axis, now we have a column matrix. For outer y, we get, what is it called? We get a row matrix. Now look at outer x dot shape 4 by 1, right? Good. Look at what is it called? Look at outer y dot shape 1 by 3. So this works, right? Because we start on the right, 1, 3. One of them is 1, so this gets stretched to 3, which is yes for our rules. 4, 1. One of them is 1, so this gets stretched to 4, which satisfy our rule. So this is going to broadcast whenever we perform our outer product operation. Okay, now let's continue. We can do outer result, and then we can do outer x multiply by outer what am I doing? Outer y. And then if we do outer result, before I press enter, let's see what this is going to give us. This should give us, this gets stretched to 3. Okay, this gets stretched to 4. So we should get a 4 by 3 matrix. Good. So we get 1, 2, 3, 4, 1, 2, 3. That's a 4 by 3 matrix. Okay. Now, there's a quicker way we can do this, which is passing it explicitly. So we can do np.outer. So this outer is a namespace in Numpy. So we do np.outer, and then we can do, in here we can pass outer result. Still going to give us the same thing. Oh crap, what did I do? Outer is missing one required, what is it called? One required position. Okay, I'm sorry. So it should have been np.outer, and then here we can pass outer x, then outer y. I think this should work now. Okay, good. So outer x, outer y. So this is doing it explicitly. So you either go with this or you go with this. So we use this namespace outer, np.outer, to do that. Okay. What else can we do? What if we try to normalize? So we try to normalize between 0 and 1. Can we try to do that? Let's see. If we have, let's have data, and then we can have let's the np dot array. So I'm going to do this using Numpy Python list. Then we can do let's have this, the first row. Let's have what should we have there? Let's have 20, let's have 30, let's have 40. That's the first row. Say the second row. Let's have 5, 15, 25. And let's have the third row. And let's get that to be 1, 2, 3, like that. Okay. So now if we have data, so we have a 3 by 3 2-dimensional array. We can try to normalize this such that the resulting array has values between 0s and 1. Now, how might we go about that? Let's declare the row matrix. Then we can do data, that mean. Then we can do axis equals 1. And then in the course of our operation, we want to keep our dimension. So we set this to true, like that. Okay. So what this is saying is, it's saying axis 1 is the column dimension. So it's saying data.mean. Find the minimum value across the columns for each of the rows. That's what it's saying. This data.mean. Remember, this is data. Now we using this what is it called? This mean method, which gets us the minimum value. So we're setting our axis to be 1. Axis 1 is the column axis. Axis 0 is the row axis. So we want to keep our dimension while we do whatever we're trying to do here. So what this is saying is find the minimum value across the columns for each of the rows that we have here. That's what this is saying. All right. Now let's also look for our row max. So this is data dot max, and then here we can do axis equals to 1 as well. We also want to keep our dimension so it doesn't truncate while this is going on. Now the reason we are doing this keep dimensions to be true is so that our resulting array is going to be of this shape. Otherwise it just truncates while this operation is going on. So this row max is, just as we had here, is looking for the maximum value across the columns for each of the rows, for each of our, sorry, what am I doing here? This is our data. Sorry, not this, this. So it's looking for the maximum value across the columns for each of the rows that we have here. Okay. Now let's do our normalization. So we can do normalized and then equals to, let's have data, this data minus row mean, this one. Okay, and then let's divide by, I'm going to open a parenthesis here, row max, then we have minus row mean. Okay, now if this works, we should get an array of this shape with values between 0s and 1. Hopefully this works. Okay, so fingers crossed. If we do normalized, good. So although what we get is of float type, but then you get the idea anyway. So we're getting this shape back, and then our values runs between 0s and then 1 point in our case, but it still agree with the idea that we started with. Okay guys, I think we've done quite a bit on broadcasting. We started with the rules, and then we went ahead to implement some scenarios to demonstrate our rules, our broadcasting rules. So guys, I think we've done quite a bit here. I'm going to stop for now, and then I'll see you guys in subsequent videos. Thanks for watching.